Hello and welcome to another exciting lecture for methods. In this lecture, we're going to be talking about reliability and validity. Now, these are mainly stats-oriented terms, but they are methodological in nature. So for this lecture, again, we're going to be talking about reliability and validity. Within reliability, we're going to have the learning objectives to define reliability. We're going to have to identify and differentiate the three types of reliability as well as how to assess each. Then for validity, you'll have to define validity as well as identify and differentiate the many types of validity. There are many types of validity that we'll be talking about. So in the last lecture, we talked about how to operationalize variables and then what measurement scale to use. Now, to take that one step further, we now must evaluate our measure. You can't just decide to use a measure and then not make sure you're using a measure that would be correct, a measure that would be the optimal way or correct measure to use. So to go about doing this, what researchers do is use two criteria for evaluating the quality of any measurement procedure that they are going to utilize. The first is reliability, and this refers to how consistent a measure is. So the easiest way to look at what reliability is does it consistently measure the same thing? If you take a test one time and take that test again a day later, is your score going to be the same or is your score vastly different? So more consistency is better. So this is the first step in evaluation. And then the second, and just as important, is validity, which refers to whether a measure is actually measuring what it's supposed to measure. I could give you a test, you could answer it, and then I could give you the same test the next day and you answer the exact same. But if I'm trying to test to see if you have depression and I'm testing instead to see if you have anxiety, it's going to have low validity because it's not measuring what it's supposed to measure. Now, the example here for whether it is valid would be a popular bathroom scale. Very consistent measure, but it consistently measures 10 pounds less than other scales. So it's consistent, has high reliability, but it has low validity because it's supposed to be measuring your weight and it's actually measuring your weight minus 10 pounds. Let's talk about reliability first. And again, like I said, this first learning objective is pretty easy. Define reliability. And it's not just define it, but be able to understand what reliability means. So reliability is stability or consistency of the measurement procedure by a specific measurement procedure. So if you're using the same procedure, high reliability means you'll get the same results over and over again. And you can look at reliability in other ways, which we'll talk about in just a minute, where you look at reliability between two measures. But in general, when we're talking about reliability of a measurement, we're talking about how stable or consistent the measurements that are produced from that specific procedure. So the concept of reliability is inconsistency or measurement of a measurement comes from error. Your measured score is going to be your true score plus error, and the more error, the lower reliability. So a scale's reliability, a measurement's reliability would be high if error is minimized. It would be extremely high if error is eliminated. You're very rarely going to be able to completely eliminate error. So even like the example on the previous one of stepping on a scale, if you step on a scale once and then you step off it and you step on it again, you're actually usually going to get two different, slightly different weights. However, most modern scales actually have a built-in memory, so they'll set you back to the same one unless a certain amount of time has passed. They do that simply because of this error factor, because a lot of them don't want you to know that they've got a small amount of error in them. So getting on the scale, getting off the scale, getting on the scale again will give you the same weight, even if it's not the same. It's only giving you the same because it's got a memory doing it. If it didn't have that memory, you'd probably have a slightly different weight. My scale, for instance, does not have that memory, and getting on the scale once and then getting on it again, and 30 seconds later, you'll be 0.3 of a pound different because, again, that error. So sources of error could be observer error. Could be what's causing this problem. So especially if you've got a scale where the measurement procedure is a person rating something. So like I've said with my dissertation, I had couples come into the lab and they sat next to each other, and then I had raters rate how close they were sitting, how often they touched. Now, if I had two raters do this, they're going to get slightly different answers because there's that observer error that comes in. Environmental changes could occur. When you're talking about weight and things like that, you're talking about pressure and humidity, and all those can actually affect it to a slight degree. Changes in participants that can occur between measures. So if you've got let's say a test of focus, the first time they do it, they might be more focused because they might start to lose focus as time goes on. So these are sources of error. These are things that lower reliability of measures. This gets us to our second learning objective, which is to identify and differentiate the 3 types of reliability, as well as how to assess each. So these 3 types of reliability. The first one is a pretty easy one. It's kind of what I've been explaining to this point, and that's what's referred to as test-retest reliability. So test-retest reliability is testing how reliable a measure it is when you go from test to test. So if it's the same test, it's higher reliability if the scores are consistent every time the measure is used. So this would be an example if I was measuring, let's say, that weight again, and test-retest reliability would be how accurate it is from the time I get on the scale the first time till the time I get on it the second time, 30 seconds, a minute, 5 minutes later. This is where you see a lot of personality tests that'll have higher test-retest reliability because people tend to score the same or very similar when they take it the first time to another time. But where you look at like psychoanalytic theory that looks at like a lot of the Freudian things, they have a low test-retest reliability when you're looking at like Rorschach ink blot tests, because somebody who takes a Rorschach test and then the next day takes it again, they're going to have vastly different scores those 2 times because it's got low test-retest reliability. The next main type of reliability is what's referred to as inter-rater reliability. I kind of talked about this a little bit already, but this is simultaneous measurements, consistent scores no matter who does the measuring. So with my dissertation, I said I have those couples in the lab. I then have coders rate how close they're sitting together and how often they touch. Inter-rater reliability is how accurately 2 raters are to each other on their ratings. So one thing I had to do to test inter-rater reliability for my study is I had a sample couple, and all of my videos were cut into 30-second segments that the coders had to rate during the 30-second segment. So they couldn't see the confederate. They didn't know if the confederate was in the room or not. That's important. All they could see was the couple. And I had a test couple that there was 10 videos that each coder had to code how close they were sitting together and how much they touched in each of those 30-second segments. And then I tested this inter-rater reliability to see if they were consistent with each other, if all of my coders were consistent with each other. And it turned out I had 4 coders. 2 of the coders were really good, 2 of the coders were not. So I retrained those 2 coders. Then I had them go back and code again, and then they were more consistent. So my inter-rater reliability, it was poor at first, but through retraining, it raised up higher. And then even after that, every single clip of the couples, I had at least 2 coders code. So at no point in time was it only one coder. It was always at least 2, and I consistently throughout tested inter-rater reliability to make sure it maintained high. And there were instances where 2 different coders drastically rated certain clips differently, and in that case I had a third coder go in and code those videos and check to see which of the 2 original coders it was most close to, and that was the rating used. So inter-rater reliability is something that, especially when you're looking at like observational research, is something that is very in-depth, and it takes a lot of work. It takes a lot of planning to make sure it's done right, because if you do it wrong, you can lose a lot of time and a lot of effort. Your study might not even be valid at all because of poor inter-rater reliability. And then the final one doesn't have reliability in it, but it has consistency in it, because remember, reliability is the consistency of a measure. This is internal consistency. That is where internal reliability is another way to say it, where a participant provides a consistent pattern of responses regardless of how the researcher has phrased the question. So the researcher will ask, basically, let's say we're trying to measure depression, and the researcher will ask them straight up, how depressed are you? Then we'll ask them a question like, how down do you feel? Or how is your mood? Or all of these different questions that are essentially asking the same thing. And this is where internal consistency will be measured, because you can't just take somebody on one word they've said. You've got to make sure that they didn't just misunderstand the question. So when you give them surveys, you've got to typically ask a question more than once in different ways to make sure that that is the actual response that the person is giving, and not just giving it due to fatigue or anything else like that. So that's internal reliability. So how is reliability typically looked at? How is it measured? How is it analyzed? I've kind of talked about this a little bit with the last slide, but one way to do it is to use a scatter plot to evaluate reliability. So to see if on a first measurement here, how they do, and then on a second measurement. And like it's saying here, this individual here, Kurt, his first measurement was 75, his second was 80. Taylor down here looks like the first measurement was about 50, the second one was about 53, that type of thing. What type of reliability is this? Think about that for a second. This is test-retest reliability, because they did the test once, then they did the test again. So it's test-retest reliability. It is possible that the measurement 1 was taken by one individual and measurement 2 was taken by another individual. In that case, it could be inter-rater reliability, but we're looking at just the easiest explanation is that these people are either measuring their own head or somebody specifically is measuring their head twice. So it's test-retest reliability. Test-retest reliability is only relevant for variables that do not change much over time. So something like mood that changes very rapidly, can change from day to day, can change from hour to hour. Test-retest reliability is typically not what would be used for that, unless you're checking something and then 5 minutes later checking it again. But typically test-retest reliability is something where you check and then you check the next day, or you check a week later or a month later. And that's where test-retest reliability will come in. And for this, again, scatter plots are good, but it's a bit more subjective than just finding a correlation. Scatter plot is just the first step to finding correlation. So as you can tell, that word there, correlation. So you can tell already that we're going to use correlation as our way to test reliability. But you've got the scatter plot, And within the scatter plot, just like when you do correlation or regression, you can draw your line of best fit. And the closer those dots are to the line of best fit, the more reliable your test-retest reliability is. Looking at example here, 2 examples of inter-rater reliability this time, where you've got Mark's ratings and Matt's ratings, and Mark's ratings and Peter's ratings. First off, this first one, they're pretty close. The correlation here would be pretty high. So that is high inter-rater reliability. However, here, this is low correlation. Like this specific one, this specific instance, you've got a 6 and a 2. Or even for Jay, you've got a 9 and a 6. Or even Jackie's even worse. You've got Mark's rating was a 2, Peter's rating was a 9. They're very different. There is low inter-rater reliability in this instance, unlike Mark and Matt's high inter-rater reliability. So again, like I said, how do we measure reliability? What is the actual measure we use? Not just looking at scatter plots, but what is the measure we use? We use the correlation coefficient to indicate the strength of the relationship. Now, there's a couple different ways we can do this. To test retest reliability, you can use a simple correlation. There's no issue there. You can just use a simple correlation coefficient. The higher the correlation coefficient, the more test-retest reliability. For inter-rater reliability, there's a special type of correlation we use, and that is called kappa. And for internal reliability, we use either split half reliability or Cronbach's alpha. Those are 2 special types of correlational reliabilities we can use to test internal reliability. Let's first look at, well, we can talk about here, you can see here, high correlation, no correlation, kind of high negative correlation, a moderate positive correlation. These are all ways that we could test-retest reliability. So in this one, it's the best test-retest reliability. In this one, it's a negative correlation. So that's would be typically a bad test-retest because they're the opposite. But if you're doing a internal consistency, or internal reliability, this can actually be something that can occur because you can have reverse coded questions. You can have one question, how depressed are you? And the next question, how happy are you? And ideally those, or typically those would have a negative correlation. And then this one here, this A is a moderate, so it would have moderate test-retest reliability, and D would have no test-retest reliability. Now that we've talked about test-retest, let's talk about internal reliability and kappa. So imagine that 2 primate researchers are trying to assess how high up in a tree a monkey was when viewing the same animal at the same time. They ought to report that the animal is at the same height. However, you're going to have issues. You're going to have issues with observational. So because they should be reporting at the same height, the extent to which they do is inter-rater reliability. Simple correlation can be used to test inter-rater reliability between 2 people who are considering a quantitative variable such as height category. So this quantitative variable, it works really good for height. However, sometimes you're not doing a quantitative variable. Sometimes you're doing a categorical classification. If you're doing a categorical classification, we can then instead use kappa as our measure. And kappa will measure the degree to which people agree on a categorical classification. So it corrects for agreement that would have occurred by chance and looks at when you've got like categorical variables where you don't have this continuous quantitative variable. Kappa can take care of that. Now, I'm not going to go into the details of how to calculate kappa. That's more of an advanced stats type technique. Just know that if you're testing inter rater reliability for an observational measure, and it's a categorical variable, what you should be using is kappa. Let's say we're trying to measure what the monkey was eating. Well, that's categorical. And you can use kappa to see if the inter-rater reliability is consistent on if both raters rated that the monkey was eating the same thing. Conversely, when you're talking about internal reliability, with internal reliability, the first thing I said is split half. And what do I mean by this? Well, one of the issues with internal reliability, if you're testing like to see how questions are from one to another, one of the issue is you can have order effects. So if you're always asking one question before another, then what you tend to get is a tendency in the second question to answer a certain way. And one of the ways you can correct for that is to test, instead of correlating the first answer to the second answer in that direction, you can test it with split half, where you do half one way and then half the other. Well, another way you can do it, which is actually a better way of doing it, is what's referred to as Cronbach's alpha. So when researchers are developing a scale, they're constantly testing for internal consistency. Why are they doing this? They want to see if all of the items are substantially correlated. If you've got 4 items on your scale, or 10 items on your scale, let's say you've got 10 items on your scale, you want all 10 items to be consistent. You want all 10 items to basically be measuring the same thing. If you've got just 2 items, that's really easy. 2 items, you just do a correlation. However, what if you've got many items? Then you've got all of the correlations. You've got the correlation between item 1 and 2, the correlation between item 1 and 3, the correlation between item 2 and 3. So when you've only got 3 items, now you've already got those 3 correlations to consider. If you've got a 4th correlation, then you're adding in 4 more correlations to consider. So, or if you've got a 4th item, sorry. For 10 items, there's 45 possible correlations. And when you're doing that, that just becomes too difficult. One of the ways they'll do it then, instead of calculating all of those correlations, is they'll do that split half I was talking about. They'll take items 1 through 5 and add them together, and items 6 through 10 and add them together, and then see if items 1 through 5 correlates with items 6 through 10. But I already talked about this. I asked, so what is the drawback of calculating a split half reliability like this? Well, what if item 5 and item 10 are correlated, but they're not correlated with 1 through 4 and 6 through 9? Well, now you've run into the issue of you're still getting high reliability, even if you've got a couple items that are not good. So what's used instead is Cronbach's alpha. So the drawback of calculating it like this, since the numbers are arbitrary, we might just as easily sum even numbers. We might sum 1 through 5. We could do all these different random sums. And because of this, we could miss minor things. We could miss those issues that would arise. Cronbach solved this problem by trying to figure out which correlations were most appropriate. And he developed what's referred to as the coefficient alpha. And it can be called Cronbach's alpha, any of these. In statistics, we use alpha in multiple different ways, but this is one of the things that originated with alpha. So Cronbach's alpha is essentially an average correlation amongst all items in the scale. So it's doing all possible split half reliabilities. And there, you'll be able to find out if one of those items is bad. When you do Cronbach's alpha, it will spit out that that item is bad. How it'll spit out is if you run a Cronbach's alpha with 10 items, and then you remove one of the items, if the Cronbach's alpha goes up, then that item is a bad item. if the Cronbach's alpha goes up by a lot. If it goes up just slightly, it's not necessarily a bad item. But if it goes up by a lot, then that's a bad item. So what you do is you test this, and there are programs that will test this for you, that will test all of your different items in Cronbach's alpha, and tells you what would happen if you removed each item individually, so you can tell if one of the items is a bad item on your scale. So looking at an example of this, so a typology of marathon runners based on cluster analysis of motivations. 9 different motivations were assessed, each with 4 to 9 items. So each motivation had its own calculation of Cronbach's alpha, indicating the extent to which the items were internally consistent. And you can see here the internal consistency, what they're talking about, on these scales range from 0.8 to 0.93. And again, higher is better, closer to 1 is better. And even retest reliability they tested here, they got 0.71 to 0.90. So this meta-analysis was basically looking at all of these Cronbach's alphas from all these different scales, saying that they ranged from 0.8 to 0.93. All of those are pretty good. There's no real issues there. Here's another example, reading about reliability in journal articles. So estimating the internal consistency, looking at coefficient alpha and test retest. And test retest they give the temporal interval too, so you can see how test retest reliability, how it is over time. You can see that this last one has 0.54 test retest over 4 years, and this one here has 0.5 test retest over 10 weeks. This one's probably not a great test retest for what they're testing, for what they're looking at. But this one, 0.54 over 4 years, that's pretty good for the amount of time that's gone by. This one also here, 0.82 over 2 months, pretty good. But then you've got your Cronbach's alpha here, your coefficient alphas, and ranging from 0.79 to 0.89. Those are all pretty high alphas. Those are pretty good alphas. These couple low ones that have a range from 0.79, it's possible that these lower ones have 1 or 2 items that if removed would bring them up in line with everything else. So that is reliability in a nutshell, and the basics of reliability. So again, reliability referred to the consistency of a measure. Validity, on the other hand, now we're defining validity, refers to whether a measure is measuring what it's supposed to measure. A measure can have very high reliability and low validity if it's measuring the wrong thing. I gave the example of the scale that's consistently measuring 10 pounds light. It's got high reliability, test retest very high, but it's measuring the wrong weight, so it's got lower validity. And there are a lot of different types of validity we can look at here. There's 2 different categories, and we'll break these down more, but there's 2 different categories. There's the subjective validities. So this is face validity and content validity. We'll talk about these in more detail in a minute. And then there's the objective validities, which includes criterion validity, convergent validity, and discriminant validity. And we'll even break down criterion validity a little bit more beyond that. So there's a ton of different types of validity. Let's actually look at those on the next slide. So we get to that 4th learning objective, to identify and differentiate the many types of validity. We'll start with face validity. If I can get back to it, we'll start with face validity. And face validity is basically measuring whether a measure appears to measure what it's claiming to measure. This is the simplest and least scientific. If I've got a few questions on depression, and it'll have high face validity if those questions look to me like they're going to measure depression. If I give them to you and show them to you and ask you, do these look like they measure depression? And you say yes, that's face validity. Face validity is the least scientific, but at the same time it is the start of validity. You should still measure face validity, you should still analyze face validity, because if something doesn't even look like it's measuring what it's supposed to, then it probably doesn't. And then content validity, the next one, is the extent to which the items on a test are fairly representative of the entire domain the test seeks to measure. So again, this is subjective, so it's not fully scientific, but let's say we're trying to get depression, and we know that there's different types of depression. We need to make sure that we've got questions that are testing all the different types of depression if we're testing depression in general and not one specific type. And that's going to be our content validity, the extent to which something is measuring the or representative of everything we're trying to measure. We are going to go over all of these in a little bit more, some of these in a little bit more detail in slides coming up. I'm kind of just giving an overview right now. Then we get criterion validity. And criterion validity can actually be broken down into two parts. But criterion validity, and now we're into the objective validities, is the extent to which a measure correlates well with a concrete outcome measure. So you can either have concurrent, which is where a new measure directly relates to scores obtained from a more established measure of the same variable. So we're trying to create a new measure for depression. Concurrent validity would mean our measure of depression, it has high correlation with an already existing measure of depression. Why would you want a new measure? Well, maybe you want a shorter measure. Maybe you want a measure that's going to include a new special question, stuff like that. That's why you would create a new measure, but you need to test concurrent validity if there's already an existing established measure out there to see if your measure correlates with that existing measure. And then there's predictive validity, which is where you check to see if your scores obtained from a measure predict future outcomes or predict behavior according to a theory. So predictive falls under criterion 2 because you're correlating, but now instead of correlating with a existing measure, you're correlating with actual behavior. So predictive validity here would be, let's say you were testing you were giving a behavioral measure and you were testing a survey measure. You would use predictive validity to see if the answers on the survey predicted their actual behavior. The next set are convergent and divergent. So they kind of sound the same. That's because that they're similar. Convergent is to see if there's a relationship between scores obtained from two or more different methods of measuring the same construct. So let's say there was convergent validity if you were looking at to see if that going back that predictive, if the actual self-report correlated with the behavioral. So there's convergent if they converge on the same thing. If those two different methods of measuring, you're measuring an actual behavior by checking to see if couples sat closer together, and you're also checking to see how they reported their desire to perform mate guarding tactics. Convergent validity would be high if they converged on the same thing, if they both measured the same thing. Divergent is where you're trying to make sure there's little to no relationship between measurements of two different constructs. And to look at it there, what we're trying to see here is if there's a difference between two different behaviors. If you're, let's say, depression, and let's say you're trying to test specifically depression that is low grade depression, and you're trying to distinguish that. You're trying to make a construct that is just that low grade depression. Divergent validity would be high if you showed that your measure was showing that low grade depression as different than the high grade depression. So there's two different constructs, high grade depression and low grade depression. You're trying to show that there's little to no relationship between the measure of those two. whereas possibly past scales show are measuring both, and they're basically the same in those other scales. You're trying to make your scale new and unique by showing a divergence or divergent validity between those two different constructs. And then finally, we get to that specific thing, construct validity. Construct validity looks at making sure that the scores obtained from a measurement behave exactly the same as the variable itself. And we'll talk about this a little bit more coming up. So that is the different types of validity. Let's look at each of these or most of these in a little bit more detail. Starting with face validity. So again, face validity is the extent to which a measure variable appears to be an adequate measure. So we can sometimes judge construct validity based on our subjective impression. Some things on their face simply look like poor measures of what they're claiming to measure. They may be right or wrong. Face validity may be right or wrong, but the point is that it is a first step. So thumb size or head circumference just doesn't seem like it could be a good measure of intelligence. So face validity can be assessed by regular folks, non-psychology experts, or even by experts. Experts use face validity. The point is face validity by itself is not scientific. Face validity is just trying to get us in the right direction. Let's use an example. So there's what's called the 2D 4D ratio. That is the length of your first or your second digit as it compares to your fourth digit. What it comes down to is the question is, or I'm not even getting to the question. Let's talk about this ratio. So you divide the length of the second and the fourth by the length of the fourth digit. So you divide your pointer finger by your ring finger. Now, what if I said something like this comment right here? The ratio is a measure of masculinity. It predicts athletic ability. It can predict personality. It can predict sexual orientation. It can predict cognitive ability. It can predict many other cognitive characteristics. What is the face validity of this? What do you think? If I say this 2D4D ratio is an accurate measure, an accurate predictive measure of all of these things here, athletic ability, personality, even sexual orientation can be predicted with this. Now, I'm going to say one thing first before you go too far. In psychology, we do acknowledge that there are no universals, or there are very few universals. So because we say something predicts it, it doesn't mean it perfectly predicts it. It means we can predict, let's say, athletic ability. If this was true, we could predict athletic ability to a certain extent, or we could predict sexual orientation with a certain degree of accuracy that is above 50%. Okay, now that that's out of the way, so we're not saying perfect prediction, we're saying prediction better than 50%. What's the face validity on this? So we're talking about face validity here. What's the face validity? And again, face validity is, does it actually appear to measure what we're claiming it measures? Now, if you know stuff about 2D 4D ratio, that may be, you may get to the answer easier. But if you don't know anything about 2D 4D ratio, then you're almost 100% going to say this is false, that this has low face validity, because it just doesn't seem like something as simple as our second digit and our fourth digit on our hand, the ratio of the length of the two of those can predict all these things. However, it's actually true. Everything there, it weakly predicts these, but it does predict these. And some of them it actually predicts higher. Let's circle this one right here. Sexual orientation. It's actually very highly predictive of sexual orientation. It is one of the biggest things we have showing that sexual orientation has a strong biological component. That it's not just a choice or anything like that, that there's actually a strong biological component to sexual orientation. What do I mean by that? Well, if you take your pointer finger and look at it, let's say I'm looking at, we've got here, and then you've got a pointer finger like this. And then, of course, actually, let me just erase that. That's actually really horrible. I am a bad drawer, but let's go like this. We've got a pinky, we've got a ring finger, we've got a middle finger, we've got a pointer finger, and we'll have that like that. And then over here we'll have a pinky, we'll have a ring finger, we'll have a middle finger, and then we'll have a pointer finger. I'm getting them a little extreme, but you see this line right here? How in the left one, the pointer finger, and this is if you hold it flat. So if you move your finger side to side, it'll change this. But if you hold your hand flat, let's say on the table, and look at this, you will see this. So we're in this case, we're looking at not like the picture, but we're looking at the left hand. So if you're looking at your left hand, this is so left hand. So if you're looking at your left hand, in the left picture here, the ring finger and the pointer finger are the same length. In the right picture, the ring finger is longer than the pointer finger, and it's quite a bit longer than the pointer finger. Can be up to an inch longer than the pointer finger, but most people it'll be between 1/4 and 1/2 inch. This is actually this differentiation, this sex difference. It's a sex difference. So it's a biological sex difference. The sex difference is due to testosterone in the womb. And I say it's a sex difference because for most biological female individuals, it'll be like this one over here. For most biological males, it'll be like this one over here. But that's not universal because in some females, they experience more testosterone in the womb, and they will then be like the one on the right. This is a masculine. So this is a more masculine. So it's a measure of masculinity. This is more masculine. This over here is less masculine. So the one on the right is more masculine. The one on the left is less masculine. And again, pubertal testosterone and testosterone in the womb influence this. So those who have more testosterone, they will have like the one on the left. Biological females who have fingers that are like the one on the left have a much greater chance of being gay. Biological males who have fingers like the ones on the left here, did I say on the right, on the left before, but like the one on the right. So biological females like the one on the right are much more likely to be gay. Biological males who are much more like the one on the left, or who have fingers like the one on the left, are much more likely to be gay. Now, it's not a guarantee. It's not a perfect prediction, but it's actually a pretty good prediction. I actually, interestingly enough, because I talk about this in developmental psych, the first time I was teaching this in developmental psych, the first time it was actually my first class I was ever teaching was developmental psych. And I'm talking about this, and I had a small summer class. There was like 10, 12 students. There was one guy in the entire class. And I'm explaining this, and I'm putting up my hand, and everybody's measuring their hand and looking at it. And the guy had fingers that were like the one on the left here. And I said, that's okay. It's not always perfectly predictive. And he's like, no, he's gay. He said he was gay. It was the only guy in the room, and he had fingers like the one on the left, and he was gay. So it does show that was a case where it came out correct. And again, this isn't always 100% correct, but it does have a lot to do with biology and testosterone, and then it relates to all of these characteristics down here. So even though this has low face validity, it is an instance where the low face validity was wrong. And that's why that's why I use this as an example. Because face validity is not always necessary for construct validity. Construct validity is our gold standard for validity. It's the validity we want the most. Face validity might get us there, but sometimes face validity will lead us in the wrong direction. Next, let's ask a question. Consider how students might respond to the following measure of racial prejudice. The first one is, I do not like Native Americans. The second is, Native Americans are inferior to whites. These are really harsh questions. Now, what is face validity on these? Are these two questions measuring what, again, they're supposed to measure what you're trying to measure. If you're trying to see in this, if you're trying to see if people are racially prejudiced, and you ask them these questions, what is the face validity of this? Face validity is actually pretty high. These are questions that would directly tell if somebody had a racial prejudice. If somebody answered they strongly agree with both of these, then that would be a very big indication that they have a strong racial prejudice. If somebody answered one with both of these, it should be that they have a very low racial prejudice, correct? That's actually not the way it works out. The problem is even though these measures have high face validity, they would likely have no construct actual validity because these types of questions people rarely answer honestly. You're going to get very few people, at least historically. More and more people are saying the quiet part out loud now, so it's changing, but at least historically, very rarely would people openly admit to being racist. At least not in the context like this. Even when the surveys are anonymous, what is found is that people don't answer honestly to questions like this. Or even if they're answering honestly as the way they view it, that is, their behavior does not reflect it. So they may view themselves in a different way than their actual behavior. So face validity isn't always necessary or desirable. Face validity is high for these. We showed a case in a minute ago where face validity was low and was wrong. Here's where face validity is high and it's wrong. So face validity is good, but again, it's only that first step. Let's then switch to talking about content validity. So content validity is that other subjective measure. And this is actually measuring the extent to which a measured variable appears to have adequately covered the full domain of the conceptual variable. All parts of your theory says it should. So an IQ test that only contained geometry problems would be the easiest example of poor content validity. Because intelligence draws on many domains. Spatial ability, vocabulary, reasoning, we've got all these domains. And yes, if you talk about IQ, if you look at IQ in a class looking at it, there's going to be instances or a lot of overlap in these different domains, but none of these domains adequately assess the whole. Even though there's high correlation or overlap in them, it's not going to be perfect correlation. So in that case, you're going to have issues with it if you only test one of the domains. Example here, development of an evolutionary valid domain-specific risk-taking scale. I actually did something very similar. I developed an evolutionary valid domain-specific loyalty scale. It was my undergrad advisor who developed this, which is where I basically got my idea from. So the purpose of his paper was to develop a set of scales or instruments to measure the extent to which people take different kinds of risks. So some people might take risks in one domain, but not in others. So some people might take risks like having unprotected sex. Others might take risks like stand up to their boss or gamble their paycheck or skydive. the issue here is, or the point. So we've got this, and again, are some people more or less likely to stick up for their own group or put down or attack those of another group? That's what um, the one type or one domain of risk that he wanted to assess, and specifically looking at between group competition. And the questions that were asked were stuff like adamantly defending the honor of your local team against a fan from a different sports team, or sitting in the section for fans of the opposing team with a group of friends while wearing your team's colors, or driving to a rival university at night and stealing the school's flag from the flagpole at the center of campus. Things like this. And what by having all of these different questions and looking at them, there's this attempt to meet the content validity to make sure that all of the different angles are analyzed. So again, going back here, we've got this issue, and that is that face validity and content validity are subjective. Does the measure seem to address all that it claims to? Some measures, they'll have poor face validity, some will have poor content validity, and they still may turn out to be good measures. Some may have good face validity and good content validity and turn out to be bad measures. Perhaps in the previous example, the responses to those sports fan items are excellent predictors of participants in things like various different types of things outside of the sports context. But because they weren't specifically asking about the things outside of the sports context, they what is needed is a validity that's based on objective empirical criteria, not these subjective impressions. And that's where our criterion, convergent, and discriminant validity are going to come in. And within those, there's the subcategories. So let's look at those. Let's start with criterion validity. Criterion validity is the extent to which a measure correlates well with a concrete outcome or measure, sometimes a gold standard. If there's a gold standard that exists in what you're measuring, then you want to compare whatever it is your scale is, whatever however your scale is designed, whatever your scale you design, you want to compare that to the gold standard. If there isn't a gold standard, you need to measure it against a scale that already exists for that theory or hypothesis. Sometimes it's not possible to do criterion validity because there's nothing out there that exists, but in general, you're always going to find something similar. And you should try and use, especially if you're developing a new scale, you should be trying to find as good of a measure as you can out there to measure yours against so that you've got some statistical backing for it. So psychologists will often use criterion validity to try and measure something roughly because it's easier than measuring it in the accepted way. It could be that the accepted way of measuring something takes hours, or is very expensive, or is very hard to do, or is very invasive. Those types of things. So you're developing a new way to measure it. You're not going to get as good as that gold standard. You're not going to get as accurate as that gold standard. What you're trying to do is get as close as possible while minimizing all of those problems with the initial measure, like it being too invasive, too time-consuming, or too expensive. And then within that, we can divide it down based on two different types of criterion validity, and this is based on timing. So if we're comparing it to something in the past, it's concurrent validity. So we're trying to see agreement between the measure and an outcome assessed either at the same time or a measure that's measured in the past. So concurrent validity would be if you've got that gold standard. So you measure that gold standard, you measure them on that, let's say, like the example up above, we're trying to see a psychiatrist diagnosis based on a complete exam. So you've got the the complete exam that was just completed, and then they do this other measure. So concurrent, it says at the same time, but rarely are they doing it at the exact same time. Concurrent, you're looking at very close in time. And then there's predictive, that refers to agreement between the measure and something assessed in the future. Now, quite often, the line between concurrent and predictive can be fuzzy. If I measure with self-report depression and then immediately do the psychiatrist diagnosis, technically that's a predictive, but they're close enough together that we would call it concurrent. If I measured the self-report and then a week later you did the psychiatrist diagnosis, then that would be predictive. Let's look at some examples. Pro sports scouts are very interested in predictive validity. They're interested in predictive validity of as many different things as they can get because they want to be able to pick out the prospective athlete that would be the best. So they use all of these different tests. That's why, like the NFL Combine. The NFL Combine is used to measure all these different things for athletes, as well as the scouts will look at their previous games, all their previous things, and they will use that to use as a predictive measure. One of the interesting things here is intelligence tests. Um, and that's how would intelligence tests predict sports outcome? Well, if you know anything about sports, you actually have to use quite a bit of intelligence when participating at a high level. Almost all quarterbacks have exceedingly high intelligence. There are some positions that require in football and other sports that require less intelligence. But most people who end up on the high end of sports have higher intelligence. They might not use it in school, but they have higher intelligence because higher intelligence is actually related to higher speed of thought. And if you've got to make those rapid decisions on the fly as something's going on, then having higher intelligence is actually one of those things that really works. It does predict. So let's look at the criterion validity between sales ability and sales, or sales ability test scores in sales, and IQ in sales. So sales ability test scores over here actually have a very high correlation, so a very high validity, criterion validity with sales. IQ scores, there's still validity here. There's still a correlation with sales. It's just a lower correlation. So it has a lower criterion validity than sales ability test scores. So when we look at this, when we would try to see what is a better predictor, it would be the sales ability test scores, not the IQ scores. Let's use another example of criterion validity. So in this case, people completed Beck's depression inventory, which is a scale that's supposed to measure depression. It's a 21 item self-report rating inventory that measures characteristics, attitudes, and symptoms of depression. When you look over here, you can see that the figure shows that people who scored on the BDI are more likely to be depressed according to clinical interviews of a professional psychiatrist. This gives us more confidence that the BDI is a valid measurement tool, meaning it has high criterion validity, because the higher someone scored on the BDI, the more likely they were to be depressed. So that's got high criterion validity. To give even more support for criterion validity of the BDI, researchers can even look at specific ranges. So if you've got, here you've got no depression, mild depression, moderate depression, and severe depression, you can see that as someone becomes more depressed, they actually score even higher for each category on the BDI score. So we can look at it as not even just a categorical measure, do you have depression or not? You can look at it as a quantitative, because the higher you score on the BDI, the more depressed you are likely to be. Next, let's talk about convergent and divergent or discriminant validity. So convergent validity, as I said before, is the degree to which or the extent to which a measure correlates with other apparent measures of the same construct or concept. So this is what we were just talking about before, as one of the parts of criterion validity is convergent validity. Does it measure what other measures of the same concept or construct measure? On the other hand, discriminant or divergent is the extent to which the measure does not correlate with measures of supposedly different constructs. Both are just as important because you want to correlate with other measures of the same construct. If you're measuring a specific type of depression, you want to be as close as possible to other measures of that type of depression. However, you want to be as far as possible, you want to diverge as much as possible with measures that are measuring something like anxiety, that are not measuring depression. So they're most often discussed in cases where there's no objective outcome like a gold standard. So we would use criterion validity specifically if we had that gold standard to compare it to. If we didn't, we'd use convergent and divergent validity in order to show that ours is closer to things that are measuring what we're measuring and far away from things that are measuring what we're not measuring. Example here, we can test if ACT scores predict college success by seeing who graduates from college. However, it's more difficult to know if a survey of creativity, yes, I can speak today, if creativity predicts creative behavior because creative behavior is difficult to define. There's no gold standard. So for ACT, the gold standard is graduating from college. Creativity, there's no gold standard for creativity. So whatever it is within creativity we're looking for, we would then see if our measure is as close to the other things that are measuring either what we're interested in or similar to what we're interested in, and diverges from things that do not measure what we're interested in. Let's look at an example of that. Self-monitoring. It refers to the tendency to pay attention to the events that are occurring around you and adjust your behavior to fit in with the specific situation you're in. High self-monitors are those who habitually make these adjustments, while low self-monitors are more likely to behave the same way in all situations, ignoring the demands of the social setting. So they're more domain general, meaning they have a general response rather than a specific response where they make adjustments to the specific situation. In 1974, Mark Snyder wanted to develop a self-monitoring scale. He initially constructed 41 items that he thought would address the conceptual variable self-monitoring. Here are some of the items I guess I put on a show to impress other people. I would probably make a good actor. I rarely need the advice of my friends to choose movies, books, or music. I have trouble changing my behavior to suit different people in different situations. So after he initially tested those 41 items, he went back and removed 16 of them because they had low item to total correlations, meaning that they didn't fit with the other questions. That's where you get that Cronbach's alpha type of thing, where you're checking the different items in it. The 25 remaining had good internal consistency and a reliability of 0.70. This is a different one of the reliability measures that's out there. It's a more primitive version of Cronbach's alpha. And then he tested people with the same scale 1 month after they first took it. The correlation was 0.83, indicating good test-retest reliability. After he had then demonstrated that the scale was reliable, he turned to the issue of validity. To show validity, he first showed that the responses to the self-monitoring scale did not correlate with other personality scales. What he wanted to show is he wasn't just measuring personality. He was measuring the specific thing. He wasn't measuring personality in general. The correlation with extroversion was 0.19 and the correlation with achievement anxiety was 0.14. So he showed that they were different. What did this show? What type of validity is this? It is divergent, and I definitely spelled that wrong, divergent validity, because he showed that it differed from the other scales. Satisfied that he wasn't simply measuring the same thing as an existing scale because of the divergent validity, he began to assess convergent validity. He went and found that his scale was highly correlated with peer reports of self-monitoring, impression of brothers in a fraternity house, that type of thing. So he looked at other things, possible ways to measure self-monitoring. It correlated highly there. He showed that professional actors scored higher on the SM scale than did hospitalized psychiatry patients or undergrads. So it's known that professional actors have more self-monitoring, and those that are hospitalized psychiatry patients have low self-monitoring. So he was able to show that. He found that high self-monitors are more able to more accurately communicate an emotional expression when reading a short monologue. So he used that as a measure. And basically from there, he was able, through multiple different measures here, through multiple different comparisons, to use convergent validity to show that what he was measuring was actually self-monitoring. So he's got this new variable, and this is doesn't just have to be the case of what we're doing. What this kind of shows what's going on with convergent and divergent validity. So you get this new measure, and this new measure is supposed to be measuring x. So this new measure here, it's supposed to be measuring x here. You can't know for sure that it's measuring x. So what you want to do is you want to basically correlate with other variables that are already measuring x. So you want it to correlate with these, but you also want it to, at the same time, not correlate with another variable. So you want it to not correlate with these. So when we look at it, you can look at here where the chart on the left provides evidence of convergent validity for the BDI. The depression inventory we talked, because it shows fairly strong correlation with another depression measure, but it's got divergent validity because it's got no correlation with physical health score. So weak correlation with perceived physical health. This shows that the BDI isn't just tapping into how someone feels in general, it's specific to their mental health. Which gets us to the question, why does the figure chart on the left show convergent validity, but the chart on the right shows criterion validity? Think about that for a minute. Why do you think the chart on the left is showing convergent validity, but the chart on the right is showing criterion validity? I mean, you do have the question. They're both showing that BDI correlates with another depression measure. Isn't it really the same thing? No, it's not. Because this one here is showing that it measures similar to another measure of depression. And it's got that correlation. This one over here is showing it to the gold standard of what depression is. That's a psychiatrist rating. A psychiatrist rating of someone having depression or not, that is the gold standard of what we would consider depression. So there's where you got your criterion validity. Because it correlates with that, we've got criterion validity. It's measuring what we say it's measuring. Because it's correlating with another measure of depression, that's actually a convergent validity because it's not the gold standard. So it's very important that you differentiate those. And the more you can show these different types of validity, the better. Criterion validity is the best. But if you can't do criterion validity, you do convergent validity. And if you can do both convergent and criterion validity, all the better. So let's finish up by talking about the relationship between reliability and validity real quick, because it's kind of going to explain reliability and validity in another way. First off, we have to ask this question. Can a measure be reliable but not valid? Meaning it tests the same thing over and over again, but it's not valid. Yes, shoe size is an intelligence test. It's reliable, but it's not valid. There's actually a correlation there between shoe size and intelligence, due to various different things. The number of children you've measured of interest in children, reliably measured, possibly valid. But when we look down here, what's going on here? Well, we've got this case when we group these together. These three cases. The middle one, it's reliable. You're consistently hitting the same area. It's not valid though because you're not in the bullseye. The one in the left is both reliable and valid. You're consistent and you're hitting the bullseye. The one on the right, it's both not reliable and not valid because you're not consistent and you're not hitting the bullseye consistently enough. Which gets you to, can a measure be valid but not reliable? No. Because if all marks are near the bullseye, they must be close together, so it must be reliable. Because even though some are actually hitting the bullseye, enough are not hitting the bullseye to trigger validity. So if you're not reliable, you can't be valid, but you can be valid and reliable, and you can be reliable but not valid. I hope that makes sense. These are the three different possible outcomes. Reliable and valid, that's what we want. Reliable but not valid, meaning we're consistently measuring the same thing, but we're not measuring what we're supposed to be. Or not reliable and not valid, because if you're not consistent, you can't consistently measure what you're saying you're measuring. You can't measure what you're saying you're measuring. We look at it as examples with the scale. If you step on the scale and over again and it tells you your weight, it's reliable and valid. If you step on the scale over and over again and it tells you 10 pounds under, it's reliable, but it's not valid. And if you step on the scale over and over again and it says you a different weight every time all over the place, high, low, middle, then it's both reliable and not valid. If it's telling you your thing consistently, then you've already met reliability. So hopefully I explained that well enough. In review, we talked about reliability. You should now be able to define and explain reliability down in details. You should also be able to identify and differentiate those three types of reliability as well as how to assess each, since we looked at those. Then validity, we talked about that. You should be able to define validity, and you should be able to identify and differentiate those many different types of validity. And then from that last slide, you should be able to talk about if something can be reliable and valid, reliable but not valid, or valid but not reliable. Thanks. Come on back.